Hey everybody, this is video 831. It's our first video talking about graphing polynomials. So this one we're just going to get a little bit of an introduction, kind of get the shapes of the polynomials and what they're going to kind of look like, and see if we can build some patterns so we have a little bit of an idea even before we type it into our graphing calculator of what each of these different polynomials is going to look like. So let's go ahead and get started. So we've got two different groups of polynomials, and that is we have an x squared graph, which we know to be a parabola, so we can write that down. Okay, it's our U-shaped graph, and that's every time we have an x squared, even if it's more than just an x squared, like x squared plus 3x plus 2, we know what it's going to look like. It's going to have the shape of a parabola. Then what about this x to the fourth graph? So this x to the fourth kind of looks like a parabola, but if you notice that this has 0, 0, it's the vertex, and then when you square 1, you get 1, but when you square 2, you get 4. Well, now we're talking about raising it to the fourth power. So 0 to the fourth is still 0, and 1 to the fourth is still 1. However, 2 to the fourth is not 4. It actually goes up much higher because 2 to the fourth power is 16. So it does carry a different shape than a parabola, even though it does look like a U. So we cannot call it parabolic, which is the phrase that means looks like a parabola. So this is an x to the fourth graph. Still very similar. Well, the other group of polynomials has a completely different shape. In fact, it doesn't have both of its ends pointing towards infinity. In fact, one of its ends is going down towards negative infinity and the other towards positive infinity. This is a cubic graph. And it kind of looks like if a car was driving and it swerved to miss something. So it has this dive to the other side. The other thought is that when you take 1 and you cube it, you get 1. But when you take negative 1 and cube it, you get negative 1. When you take 1 and raise it to take 2 and raise it to the third power, you get 8. But when you take negative 2, you're going to get negative 8 way down here. So you end up with this symmetric, but it's not right over the vertical axis. It's kind of on a diagonal that you can see what's happening. So the input is positive, you get a positive result. If the input is negative, you get a negative result. So this is a cubic shape. Well, if we talked about x squared and then I move to x to the fourth, what's going to happen when we talk about x cubed but we move to x to the fifth? Well, the graph doesn't change very much, except that just like the x to the fourth, it gets bigger a lot faster because you're raising. See, this 1 and negative 1 stays the same, but it's the 2's and you go, wow, 2 to the fifth power shoots way up to 32, and negative 2 to the fifth power shoots way down to negative 32. But in general, the shapes are the same. So you can imagine that if I went to x to the sixth, that it would look similar to this parabola and these x to the fourth graphs. And if I went x to the seventh, it would look similar to these odd exponents. Well, so now we're going to talk about not just the shape, but the end behavior of these. When we talk about end behavior, we're talking about as x grows infinitely larger, what happens to y? But we also want to consider looking at if as x grows infinitely smaller, as in towards negative infinity, what happens to y? So it is the same question twice, and this happens to be that as you take x's keep getting bigger, your y values are going towards positive infinity. But as your x values get really small, your y values are still going towards infinity. So the way we write this is we say as x goes to infinity, y also goes to infinity. Well, that only addresses one side of the graph. You see, that only addresses this side. As x is getting bigger, y is going towards infinity. What about the other side? So as x is getting smaller, oh, y is still getting bigger. So we write this twice, but we're talking about going towards positive infinity. Then we say as x goes to negative infinity, and y also gets bigger. Well, what about odd polynomials? We're still using the same idea for end behavior. As x is getting larger, as x is getting smaller, what happens to y? But we notice that the shapes over here looked like this for the odd degree polynomials. These are odd degrees. Odd degrees. So as we get bigger here, we're going to write this the same way. As x goes towards positive infinity, so as we're moving this direction, what is y doing? And we can see let me grab the other color. As we're going this way, y is going up. So that's how we write it. Y is going towards positive infinity. Well, here's where it's different. As x is going to negative infinity, which is kind of like going left, as we're moving left, what's happening to y? Well, as we move left, y is going towards negative infinity. So this is how we write and describe our end behavior. The ends are as in, if you walk to the left or if you walk to the right, what is the y doing? Are you looking up or are you looking down? So maybe write those words down. As you walk to the left or the right, are you looking up or looking down? So the beginning is as you walk to the right, you look up. That's how we're describing it. So you're talking about walking left or right, but your answer about the y values are looking up or looking down. That's the positive infinity and negative infinity. Okay. So we've got two examples here, and what I'd like you to do is grab your graphing calculator, pause the video to make sure you got time, but I want you to type in this first example into your graphing calculator so we can look at the shape. Now you may already have predicted the shape, but I want you to see it on your graphing calculator and what it's going to look like. So pause now and give that a try. All right, so once you've seen it on your graphing calculator, and you see the picture of the shape, okay, you notice it looks like this. And that -2 is showing that it moved down 2, and that's the intercept that you get. It kind of almost looks flat right there. So if we're describing the end behavior of this graph, we would say as x goes to positive infinity. Now what I just said was as x goes to the right. Okay, as x goes right, y goes to positive infinity. That's saying y goes up. Now we go the other direction. As x goes to negative infinity, which means left, y is going down. That means negative infinity. So this is the end behavior. Let's take a look at the next one. And I want you to go ahead and type that one in your graphing calculator as well. Don't forget the parentheses. And when you've got that graph, go ahead and join me again. And you can see that this one kind of looks like a U, but it's not a parabola because it's not x squared. And you can see it looks like, oops, probably crosses the axis right around there. And it looks like this. It almost looks flat again on the bottom. So we're going to be talking about as x goes to the right, which means positive infinity, y is going up. But as x goes to the left, which means negative infinity, y is still going up. The last thing we're going to consider is what if you reflect these? What if you flip it over? So I want you to think about that on your own. And think about how would you write it. And I'll tell you, your x part stays the same. So as x goes to positive infinity, I want you to describe what y is doing. And as x is going to negative infinity, I want you to describe what y is doing. And I want you to do that for both of them when you consider what happens when you reflect them over, as in when do you put a negative in front. So you may use your graphing calculator to assist you in doing that, and then we're going to check back in with each other about how to complete those statements. So you're writing a statement for each of these when you flip them over. All right, guys, great job.